Hi, welcome back to the Quantum Rings Quantum Summer School. Today we're going to be getting comfortable with some of the foundational building blocks of quantum algorithms, quantum oracles, and amplitude amplification. These are some of the key ingredients that we need for the complex algorithms that we're going to cover later in the course. Let's get into it. So the first thing we want to talk about today is quantum oracles, and then after that we're going to talk about amplitude amplification, which is actually going to build upon what we talk about with quantum oracles. Before we talk about what an oracle is, I just want to talk a little bit about what the input looks like for our quantum computations. So classically, we would have some function, f of x for instance, that outputs y. And in this case, both of these things would be a bit string. So for example, x could be 0, 1, 1, 0, 1, or something like that. For a quantum computer, the input looks a little bit different. Our input is a wave function, and the wave function is a superposition of basis states which encode bit strings. So for instance, in the case of 2 qubits, we can have our psi, where it's a linear superposition of the state 0, 0, 0, 1, 1, 0, and 1, 1. And each of those basis states has some amplitude associated with it. These C's out front here. More generally speaking, for an n-qubit state, we can write psi as a sum of a superposition of all the bit strings of length n. So to express that in a compact notation, we could do this. So this here is just the set of all bit strings of length n. So for instance, if n was 3, then this would be the set 0, 0, 0, 0, 0, 1, 0, 1, 0, and so on. And then each one of those states is going to have an amplitude associated with it. And then we can just put the bit string in the ket. So generally speaking, our inputs for quantum computation are superpositions of all the bit strings of length n. So what do we put our inputs into? Well, one thing we can do is use an oracle. And an oracle is essentially a black box. It performs some sort of computation or does something useful. We don't know exactly what's going on inside of it, but basically we can query it and get some result out. So a couple of main things to know about oracles. So one is that oracles are unitary operators. And the reason for that is they're composed of quantum gates. And we know that all our quantum gates are unitary and reversible, so our oracles, which are just composed of gates, should also be unitary and reversible. And then the role of our oracle is either to perform a computation, or it could also mark a correct answer. And we're going to take a look at an example of each of these today. So the first example I want to talk about is an oracle which performs the following operation. So it takes as an input 2 qubits, and the top qubit it should do nothing to. So we have x coming in and x going out. And then on the bottom, we should get this output here, f of x plus y, where this plus is addition mod 2, or binary addition. So that just means, for instance, 0 plus 0 is 0. If one of them is 1, it's 1. If both of them are 1, it becomes 0 again. So basically, this oracle encodes the function f, because we can back out what f of x is from the result f of x plus y. So let's take as an example this function, which is f of 0 equals 1 and f of 1 equals 1. So it just always outputs 1. And let's think about what the results will be in each of these 4 cases. So f always outputs 1. So we basically just need to add y with 1. So 0 plus 1 is 1, 1 plus 1 is 0, 0 plus 1 is 1, and 1 plus 1 is 0. And now let's think about how we could construct an oracle that performs this operation. So we know that our x state is going to remain unchanged over the course of the operation. And something should definitely happen to our y state, because we can see that f of x plus y does not equal y. And in fact, what we see is that f of x plus y is the exact opposite of y. So this is indicating a bit flip, and if we just apply an x gate on y, that's exactly what we'll get. We can do another example where f of 0 is 1 and f of 1 is 0. So in this case, when x is 0, f is 1, so here f plus y is going to be the opposite of y. And then in the other case, f of 1 is 0, so we're just going to get y here again, so 0 and 1. And now let's think about what we can do. So now we can see that there's definitely a difference between when x is 0 and x is 1. And think for yourself about what gate might be useful to do something different in the 0 state versus the 1 state. So if you were thinking of the C0 gate, that's really good. We want something that either only happens or only doesn't happen when a state is 1. So that's a controlled gate. So if we put a controlled x here, that gets us most of the way to what we want. So then in the case of when we have the input 0, 0, that would give us an output of 0. 0, 1 would give us 1. 1, 0 would give us 1. And 1, 1 would give us 0. So what that tells us is that we need to apply another bit flip here, and we'll get exactly what we want. Another type of oracle that will be very useful to us today and in the future is the phase flip oracle. And the phase flip oracle basically just flips the phase of a certain state or states. So if you have some input state psi and your oracle flips the phase of the basis state y, then our new state psi prime would just be minus cy y plus the sum of all the ones that are not y normally. So now let's move over to the coding notebook. First thing, just import all the libraries that we need. And then we have some helper functions here. This is just a truth table generator for our oracles, so we can check out easily if they're doing what we want. And first, let's just do some practice with conditional gates. So basically, when we want to perform some quantum logic, a lot of times what we want to do is manipulate a qubit or qubits conditional on the state of another qubit or qubits. So let's practice doing a couple of these. And then one thing that we want to keep in mind is that we don't want to alter qubits that we don't want altered in the end. So we can leverage the fact that our gates are unitary and reversible. And so if we have to apply a gate in order to realize a controlled gate, then we can apply that gate again or its Hermitian conjugate to cancel it out in the end. So here in the first one, we want to make a 3-qubit circuit which applies an X gate to qubit 2 if and only if qubit 0 is 0 and qubit 1 is 1. And as with all of these, I encourage you to try it yourself. I will walk through it, but definitely think about it for yourself and see if you can get an idea. So one thing they should definitely bring to mind is the double controlled X gate, because we want one qubit to have a bit flip if and only if something is true about 2 other qubits. But the problem here is that we want it to be when qubit 0 is 0 and qubit 1 is 1. And the way that the controlled X gate works is it flips the target if and only if both of the qubits that are controls are 1. So what we need to do is we need to apply an X gate to qubit 0. And this X gate ensures that if qubit 0 started in the 0 state, it will trigger the double controlled X. So controlled on 0 and 1, targeting 2. And then, very important, we want to make sure that we undid whatever we did to qubit 0, because we didn't actually want to alter its state, we just wanted to manipulate another qubit state based on that qubit. So that's what our circuit would look like. Now we can make a 3-qubit circuit, which applies an X gate to qubit 1 if qubit 2 is in the plus state, and then applies a Z gate to qubit 0 if qubit 1 is in the 1 state. Okay, so let's start with the first part. We want to apply an X gate to qubit 1 if qubit 2 is in the plus state. So again, we want to use a controlled X gate, but we want to make sure that if it's only triggered when qubit 2 is in the plus state. So what we need to do is rotate the plus state to the 1 state. So how can we do that? Well, if we apply a Hadamard gate to qubit 2, that will send the plus state to the 0 state, and then we can apply a bit flip to qubit 2. So now if qubit 2 is in the plus state, it will be in the 1 state, and now we can apply our controlled X. So that will be controlled on 2, targeting 1. And, very important, we need to undo what we just did to qubit 2. So we first undo the X gate, and then undo the H gate. And then finally, we want to apply a Z gate to qubit 0 if qubit 1 is in the 1 state. And do you remember what this gate is called? Yeah, this is the CZ gate, or controlled phase gate. And that would be controlled on 1, targeting 0. So this would be our circuit. And I just want to point out the appearance of this here, which you'll see a lot in quantum algorithms, where you have some sort of mirror-looking behavior. So we have this H and then X, and then a controlled gate, and then X and then H. So it's kind of like we did something, applied a controlled unitary, and then we undid it. This happens a lot in quantum algorithms. So now let's talk about our oracles. Our oracle is basically a black box which is going to perform some sort of computation or transform a quantum state. And we already talked about 2 kinds of oracles today. So one is the addition oracle, where we have some function f of x, and then it is outputting f of x plus y, where y is an auxiliary bit that we're using to help us out. So let's talk about that one first. So here we have an example of a function f which always outputs 0. We did a similar version of this already when we did the function that always outputted 1. So how do we turn this into a quantum oracle? The first thing we can do is build 2 quantum registers. So we want a quantum register called QX, which is going to have 1 qubit, and a quantum register called QY, which is also going to have 1 qubit. And then we need to make a quantum circuit out of these 2 registers. So if you look at our inputs and outputs, we can see that whatever y is, f of x plus y is the same. So what that tells us is that we actually don't need to do anything at all. If we just don't apply any gates, we're going to realize that oracle. And we can check ourselves on this with a truth table. We can define our oracle here, which takes in as arguments a quantum circuit, the register x, and the register y. And then we're just going to apply some gates in here. So for instance here, we don't actually want to apply any gates, so we can just do nothing. And then we can check our truth table. So here we have all of our inputs and our outputs, and we can see what the results of f plus y is. And we can see that it lines up with what we expected. So here we can do another example where f of 0 is 0 and f of 1 is 1. And now we can try and build the oracle for this. So you may remember before we were talking about another function very similar where f of 0 is 1 and f of 1 was 0. And this is the exact inverse of that. And for that one, we used a controlled NOT and an X gate. And so for this case, we just need the controlled NOT because the X gate is that additional bit flip that we don't need. So we want to be controlled on QX, targeting our qubit Y. We can check that this works. And our truth table looks how we expect, so that's great. So here's a couple more exercises for you to try on your own, and you can check that it's working with the truth table. And then if you feel like a challenge, there's also another problem you can do, which is try to make an oracle for a case with 2 inputs. So the input bit string is length 2, and see if you can do that. Okay, so now let's talk about our phase flip oracle. The phase flip oracle flips the phase of a certain state. In order to understand how this works, let's just start with a 2-qubit example. And we're going to consider a 2-qubit system with a target state of 0, 1. So the oracle should flip the phase of the 0, 1 state. And I'm just going to change the ordering of the bit string here to match Qiskit's bit ordering. And then our number of qubits is the length of the target state. So we're going to make a quantum circuit with the right number of qubits, and the first thing we're going to do is apply a Hadamard to all the qubits so that we can be in an equal superposition state of all bit strings of length 2. So let's do a Hadamard, and we want to apply this to all of our qubits. And then we want to find the indices of all the elements that are 0 in the bit string and flip them. So remember that the rightmost bit is the least significant bit, and the leftmost bit is the most significant bit. So in this case, the 0th bit is 1, and the first bit is 0. So we actually want to apply an X gate to the qubit of index 1. And now we can print out the state vector at this point in the circuit. So we have an equal superposition of all states, 0, 0, 0, 1, 1, 0, and 1, 1, and the fact that we performed a bit flip on one of the qubits doesn't impact this at all. But now we're going to apply a controlled Z gate. And what the controlled Z gate is going to do is it's going to flip the phase of the state, which is the all 1 state. If we expand this to more than 2 qubits, instead of just having a controlled Z, we would have a multi-controlled Z with all of the qubits involved. And that would just flip the phase of the all 1 state. So here we can do the same thing as before, but now we also want to apply a CZ. And now we can see that the phase on the 1, 1 state has been flipped. But this is not exactly what we want. We want it to flip the phase on the 0, 1 state. So if we want to do that, then what we need to do is flip one of these ones here, in fact the leftmost one, and that will put the phase on the 0, 1 state. So now repeating all these same steps again, but now adding on the final bit. We just need to flip back the first qubit. And now we've picked up the phase on our 0, 1 state, which is exactly what we wanted. So the basic premise here is to flip the phase of the all 1 state and then use X gates to flip the 1s to 0s in the locations that you want. So follow the same approach and you can construct an oracle for other target states. You can also expand this to a 3-qubit system by using the double controlled Z gate, so CCZ instead of CZ. So you should try that. So this brings us to our last section, which is amplitude amplification. And the reason this is really useful in quantum computation is that we know that our measurement results are probabilistic. So it isn't like a classical computer where you say, oh, here's two numbers, multiply them for me, and it gives you one answer. You instead get some distribution of probability amplitudes. And what you really want is the amplitude of the correct answer to be as big as possible, and the amplitudes of the wrong answer to be as small as possible. So this way, hopefully, if you do a few measurements, you should have a pretty good sense of what the right answer is. So let's talk about the steps of amplitude amplification. So the first step is we want to create an equal superposition of all basis states. So think for a second about how you would do this. So the Hadamard gate is our favorite tool for creating superposition. So if we just apply a Hadamard gate to every qubit, then we'll end up with the equal superposition state. So more specifically, this will be 1 over root 2 to the n, sum over all the bit strings of length n. And now we can consider what the distribution of amplitudes looks like at this point in the circuit. So let's say that the state that we're trying to amplify, our correct answer, is y. So we know that currently all of the amplitudes are equal. So we have this state, this state, this state. All of the states have the same amplitude, which is that 1 over root 2 to the n. And let's say that this state here is our state y that we want to amplify the amplitude of. The next thing that we're going to do is apply a phase flip oracle, which is going to flip the phase of y. So after that point in the circuit, all of these amplitudes will be the same, except we'll just have a minus sign on this one. And then we're going to apply a diffusion operator. And a diffusion operator flips all of the amplitudes over the mean of the amplitudes. So let's look at before we apply it, we have something that looks like this. And we can say that the mean of the amplitudes lies somewhere in the middle here. It's not at the height of all the other ones that aren't y, because y is dragging it down a bit. And now we want to flip over this mean amplitude. So what's going to happen is all these other states are going to get a shorter amplitude, and our state y is going to shoot up and get a bigger amplitude. We're going to learn about this in more detail in future episodes, for instance, how you go about constructing a diffusion operator, but for now, just take my word for it that you can do such a thing, and we're also going to look at it in the coding notebook now. Okay, so let's build an amplitude amplification circuit. So first thing we want to do is create an equal superposition of all basis states. So here we want to apply a Hadamard gate on all of our qubits. And in this case, we can apply it to all of the qubits in our quantum register, which has 3 qubits. And then I just have a barrier here to keep things somewhat clear. And then we can have a phase flip oracle. So we can just follow the same technique that we did before. So let's say we want to flip the phase of the state 101. Then we should apply an x gate to qubit 1, because 101 has only 1 0. And then we should apply a controlled Z on 0, 1, and 2. And then we should apply an x again on qubit 1. So there's our phase flip oracle. And then here's our diffusion operator. Basically, we're going to apply a Hadamard to all the qubits, an x to all the qubits, and then a double controlled x sandwich between Hadamards, and then x's again and Hadamards again. So you can see again it's that like mirrored kind of behavior where you're doing something on one side, then a controlled unitary, and then undoing it on the other side. And then the last thing we want to do is measure. So here's what our circuit looks like. We've got, at the beginning, our Hadamard's putting everything in equal superposition. We have our phase flip oracle here, and then we have our diffusion operator here, and then finally we're measuring. So let's run this 1,000 times and see what we get. And what do you know? The state 101 has the biggest amplitude, and that's the one that we were looking for. One question that we might want to ask is, what happens if we repeat the amplitude amplification process again? So let's try that. If I grab from here all of this, and bring it down here, and then we don't need to repeat the part where we create an equal superposition. We just want to repeat the part where we do the phase flip oracle and the diffusion operator. So basically, we have this situation here, and then we want to again flip the phase of the 101 state, and then flip that again over the mean of the amplitudes. You may be able to see that this is going to enhance the amplitude again. So let's see. So this looks kind of crazy, but now if we run this again, now we can see that the 101 state has an amplitude of almost 1, and everything else has an amplitude of almost 0, which is exactly what we want. So I encourage you to play around with this. You can try making other phase flip oracles and see if you can target other states. Another thing you can do is check what happens if you repeat the amplitude amplification more than 2 times. So what if you do it 3 times or 4 times? Another thing you can do is you can make an oracle for more than one target state. So if you want to do that, you just make an oracle for one and the other and just put them together. So just to give you an example of how that would look like. Here I had a phase flip oracle for the state 101. We can make a different one, let's say for 110. So now I just have 2 oracles next to each other. And now if I run this, now the 101 and 110 states have the highest amplitudes, and actually in this lucky instance, the amplitudes of all the other states have vanished. So again, I would encourage you to play around with this. We're going to be using oracles and amplitude amplification again and again throughout this course. So today was just to get a feel for it, and then we're actually going to put it to use in the future. Well, that's all for today. I hope you enjoyed learning about some of the building blocks of quantum algorithms. We're going to use amplitude amplification and oracles throughout this course. And next week, we're going to tackle 3 algorithms: the Deutsch-Joscha algorithm, Simon's algorithm, and Bernstein-Vazirani. I'll see you then.